Okay, students, hope all of you learn what are things we have taken in last class. Last class we studied about this radioactivity. Okay, three kinds of radioactive particle, alpha, beta, and gamma. See, gamma we can say as particle. It's a radiation. So mainly we study about alpha, beta as a particle and gamma radiation, charge, penetrating power, mass, everything we have studied last class. Okay, we compare all these things. Then ionization power, how they ionize the gas, few topics. Then we studied about this few properties, isotope, isobar, isoton, uses of radioactivity, medical use, scientific use, industrial use, sources of radiation and harmful effects of radiation. These are the things we studied last class. Today we are studying about the safety precautions. What are the safety precaution we need to take by running a nuclear power plant or by using nuclear energy? First you start with the safety measure while establishing a nuclear power plant. Okay, where we need to place a nuclear power plant, where we can establish a nuclear power plant. First thing is that, ensure that people working in it are not exposed to nuclear radiation. Okay, the people working inside the nuclear power plant should be safe. In case of any accident, there is a minimum spread of radiation. Okay, one more time, two things. People working inside should be safe. Then any accident, in case of any accident, minimum spread of radiation. Two things. Then the nuclear reactor of power plant, the nuclear reactor of the power plant is shielded with lead and steel wall. See, this lead is a special element. It has a unique property to stop radiation. So that's why we are building the walls with lead and steel to stop radiation. So they stop radiation to escape out from the power plant. Next one is that the nuclear reactor must be housed in a airtight building. Okay, the reaction should be taken place inside a airtight building of stone concrete structure, which should withstand earthquake, fire and explosion. One more time. Listen. The nuclear reaction should be take place inside a concrete building, airtight building. Okay, should be a strong concrete structure. Nuclear reaction should be take place inside a strong concrete structure. What is special of this concrete structure? See that they can withstand earthquake, fire and explosion. Next precaution, there must be a backup cooling system. There should be a backup cooling system. What's this backup cooling system? What's special of this? In the case of any failure in one of the system, see, any failure in the system, the backup cooling system will be activated and save the core from heating and melting. Okay, one more time. There should be a backup cooling system. Somehow any kind of accident or any kind of failure occur, the cooling system activated, then which prevent the core from heating and melting. Okay, mainly 4 safety measurements while establishing a nuclear power plant. 4 safety measurements to establish a nuclear power plant. Started with the first system is that people working in it are not exposed to nuclear radiation. Okay, people working inside nuclear power plant are not exposed. Make sure that they are not exposed to nuclear radiation. In the case of any accident, there is a minimum spread of radiation. Whatever may be the accident occur, the radiation should be minimized. Second one, nuclear power plant must be shielded with a lead and steel wall, so it can stop radiation escaping out. Next, nuclear reactor must be housed in a airtight building. The reactor should be placed in a airtight building. So what specialty of that building? It can withstand earthquake, fire, and explosion. Then we can go to the next one. There should be a backup cooling system. There should be a backup cooling system. In case of anything go uncontrolled, a cooling system activated, which helps the core to get heated and melted. So, it's a safety measures while establishing a nuclear power plant. Next is safety measurement by handling radioactive materials. Okay, what are the safety measurements to take while handling radioactive materials? Next thing. First of all, see, there should be a special lead. See, always we handling with the lead. Okay, so there should be a lead line parts and lead glove. Okay, see, everything we cover with the lead. To handle it with the lead. Okay, we are taking with the lead and our hands are covered with the lead glove. There should be handle the radioactive materials with the long lead tongs. See, we are handling radioactive material with a long tongue. Okay, so long gloves, long tongs, everywhere, everything is made with the lead. Then there should be a safety limit of radiation. Okay, for each person, there is a minimum number of radiation, there is a maximum number of radiation a person can withstand. So, thing is that this is special film bandages are there, which can dictate the amount of radiation. So, a special film bandages are used to test from the time to time to know the amount of radiation for each particular person has exposed. Okay, there should be humans work inside the reactor. So they wear a special bandage. That bandage record the amount of radiation which that person exposed. So make sure that the amount of radiation exposed to the human is less than the safety limit. Then the radioactive substance must be kept in thick lead container. See the radiation, there should be radiation source. They should keep in lead container with a narrow opening. What's the advantage of it? Which prevent the radiation to move in other direction. You have to make sure the radiation are moving in a particular direction only. So should be kept, the radiative substance should be kept inside the lead container with a narrow opening. So there are the 4 points to take care when handling a radioactive substance. Okay, first 2 points are lead, see, it's lead glove and lead, everything is made with lead. Second is then there is a proper measurement for the radiation, for the person who handling with the radiation, then should be kept in a lead container with a narrow opening. And other thing, safety method. See, after the reaction, there should be nuclear waste should be there. What is the thing left after reaction? That is nuclear waste. So the radioactive material after its use is known as nuclear waste. The radioactive material after its use is called as nuclear waste. So we should care about this nuclear waste also. How we can take care of it? If you expose to any open place means the continuously emitting radiation. So imagine if after the use, if you kept the radiation here. See that element, substance will continuously emit radiation, harmful to all the persons inside this room or inside this building. So we should make sure that it should disperse properly. How can you make that? See, first of all, we make cakes. Okay, we need cakes with that nuclear waste. Okay, see, nuclear waste should be, we can obtain nuclear waste from laboratories, hospital, then nuclear reactor. Okay, like that, nuclear waste is possibly nuclear waste is there. So first of all, we make them into cakes, then we place them in some, there is a deep underground storage. We kept them in deep underground stores. One more time, we make the nuclear into cakes and keep them in deep underground store. What does it mean, deep underground store? There will be mines. You know what mines means? Petroleum mines, coal mines are there. So after the use of mines, we can use that space to dump this nuclear waste. We can dump these nuclear cakes. Then after that, we can cover its top. That's one way of removing these mines. After that, we seal the mine for storing this cake. So one method of dumping this nuclear waste. Okay, so in this way, see, safety should be, make sure the safety should be there in all these three stages: establishing, handling, and removing the nuclear waste. All these three stages, you should make sure that a proper safety measurement should be taken care of. And one more thing you should know, that even though if you take all this measurement, still there is a possibility of radiation. It's called background radiation. Background radiation. There are two kinds of background radiations are there: internal source and external source. For each and every human being, two kinds of source are there: internal source and external source. What do you mean this internal source? See, inside our body, it's a carbon 14 isotope, potassium 40, carbon 14, potassium 40, carbon 14, 14. So all these two isotopes are radioactive. These two elements are there in our body. So there's a possibility for obtaining radiation inside our body, source which kept inside our body. Another source is an external source. External source means the cosmic rays. There are some cosmic rays are possible occurring, space, radiation from space. There are some cosmic radiation from space, mainly sun or any other source. Radiations are reaching our atmosphere, maybe they can reach our body also. So we can't keep 100% safe from all this kind of radiation, but we can at least take safety measurements to avoid its dangerous effects. Okay, so students, small chapter, small section. Okay, it's a small section. Section A is over. Now we are going to section B. Before starting section B, any doubts you can ask. Okay, any doubt regarding section A you can ask now. Students, regarding section A, radioactivity, three kinds of radioactive particles, then its properties, safety. Okay, any doubts? Hand for any doubts? Okay. Students, we can go to next section. Okay, in this chapter, section B, nuclear fission and fusion. Okay, hope you remember this Einstein's famous equation, E equal to mc square. Okay, what does equation means? E for energy, mass, C speed of light. See, this equation is say that energy can be converted into mass and mass can be converted into energy. Okay, both are same thing. Okay, when energy converting into mass is speed of light 3 into 10⁸ and square, it's a big number. When the energy is converting into mass, the amount should be reduced. But reverse, if you convert mass into energy, we obtain a big amount of energy. So this E equal to mc square is equation which gives how we can change mass into energy and energy into mass. How much energy we can obtain when mass converted into energy. How much energy how much energy we can obtain when mass converting energy, or how much mass we can obtain when energy converted into mass. So that relation will obtain from this equation E equal to mc square. See, in the case of nuclear reaction, this equation is very important because in this nuclear reaction, see this fission, especially nuclear fission and fusion, the mass is converting into energy. If mass is converting into energy means the amount of energy released is a huge number. When mass is converting into energy means there's a huge amount of energy is being released. Mainly two processes, that is fusion and fusion. It means, see, one AMU, one atomic mass of mass, atomic mass unit, one AMU of mass equal to 931 mega electron volt. So it's big number. So one atom, you see, I know atomic mass, very small amount. So that amount of mass can be produced 931 mega electron volt. So when mass converting into energy, it's become a big number. When a mass converting into energy, it's become a big number. It means when we convert mass into energy, we are obtaining a large amount of energy. Okay. So related to this, we can study two processes regarding this process of nuclear converting mass into energy. Nuclear fission. We are starting with the nuclear fission. Okay, I will show you a video regarding this nuclear fission. Okay, we are starting with the nuclear fission. Okay, students, we can go through this again.
Nuclear fission is the splitting of a heavy element.
Okay, uranium, as you know, have highly mass compared to the nucleus. Is a heavier mass element. Mostly most of the heavier mass elements were nuclear for nuclear fission. Okay, this heavier mass element
nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium
in the presence of a neutron. Okay, the heavier mass element in the presence of a neutron
35 is initiated when a neutron traveling with enough velocity collides with a uranium.
See how many products are there? Two daughter nucleus are there. A heavier nucleus bombarded with a neutron. Two new nucleus are being formed. Okay, kryptonium and barium. Two new nucleus are being formed. Along with this, three other neutrons also. Okay, one neutron to trigger the process and other three neutrons are be released by this process. Then along with two daughter nucleus, three neutron plus energy. These are the products. Okay, when a heavier nucleus hit by an accelerated neutron, two daughter nucleus, three neutron and energy is being released. Let us see what happened to this neutron.
235 nucleus. The collision produces U-236, which immediately splits into two lighter elements such as krypton-91 and barium-142. The fission event also releases three neutrons and energy. The three neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of massive amounts of energy in the form of heat, light, and ionizing radiation, an atomic explosion.
See, fission, it means splitting. It means splitting. Hope you got the idea of the process. See, a nuclear fission is a process in which a heavy nucleus split into two daughter nuclei, nearly same size, by bombarding it with a slow neutron. When a heavy nucleus bombarded with a neutron, they produce two daughter nucleus, 3 neutron plus energy. These 3 neutrons again go to collide with the other nucleus. Again, all these 3 products will repeat again. This process will carry on till each and every atom being used. Within very short time, the whole amount of substance will be utilized and produce energy. So, a huge liberation of energy will occur in this process. Okay, remember, see that equation also, you should by heart the equation. Remember, hope you remember the equation which you have seen. See, uranium 92 to 35. In the presence of a neutron split into barium 144, okay, mass number 144 and atom number 56. What's the other krypton? Kr krypton. Okay, other nucleus krypton, mass number 90, 89 and atom number 36 and 89. Okay, what are the other things? Plus 3 neutron plus energy. So this process together we can call as the single fission. Okay, single fission process like that. We can't make a single fission as alone. There is a minimum amount in liquid. See, if you take only minimum amount, then only the process will start. So we can't take each and every atom and make energy from it. A minimum amount is required. Then only the reaction will start. After that, the reaction will carry out within seconds until each of the uranium atoms or the fuel be used. We can use this in 2 manners, controlled or uncontrolled. A controlled reaction we are using in nuclear reactor. How we can control this reaction? See here, it's a control. See, the triggering is occur in the presence of neutron. So we can remove or slow down this neutron. We can control the reaction up to a level. So by using the neutron, there are some substances which can absorb neutron. So we try to remove the neutron or slow down the neutron. We can reduce the time or we can slow down this process. That is used in nuclear reactor. Controlled chain reaction. Okay, the product of one reaction triggering another one. Then again, products of neutron triggering another process. Like that, the chain reaction is going. So, if we can control the chain reaction, it's used in nuclear power plant. But it's uncontrolled. It's an atomic bomb. Uncontrolled nuclear reaction is an atomic bomb, which once worked in Hiroshima and Nagasaki. It's an uncontrolled nuclear fission reaction. Okay, so this controlled reaction used in constructive purpose for obtaining energy. Large amount of energy you are obtaining from small space, small amount of fuel. So that's a constructive way, it's good, but destructive way, make a large explosion and making, see, still the people living in Hiroshima and Nagasaki suffering its effects till now also. So the for ages, for years, the effect should be there. What's the effect of a nuclear reactor? See, the after explosion also, the substance will produce radiation. Means the radiation will affect for generations. Okay, so not only see initial effect, initially the explosion will cause at least for miles. Other than that, it affect for generations. Means it's a uncontrolled reaction, means nuclear fission, uncontrolled reaction will affect for generation. Okay, so we can use in constructive way and destructive way. Both the ways a chain reaction. We can slow down this chain, say controlled one. Uncontrolled process become nuclear bomb, nuclear fission bomb. But how this energy is obtained? How this energy is obtained? Like question is here. If you take this mass of uranium nucleus, then if you add the mass of all these three, means barium, krypton and neutron. Okay, see, if you add these three and compare with this one, here uranium should have more mass. Uranium nucleus have more mass than all these three products combined together. The missing mass is converting into energy. Actually, here mass is converting into energy. Previously I mentioned mass can be converted into energy from Einstein equation. So when we are converting this mass into energy, see, a majority of the mass is here. Barium, krypton and neutron, they carry most of the mass. But a small portion is missing. The missing mass is converting into energy. That energy is being released. But when mass is converting into energy, the amount is huge, heavy. That's why this much energy is being released. Okay. So huge amount of energy is being released in each atom. So together, so big explosion occur in this process called nuclear fission. Okay, so constructive purpose, nuclear reactor, nuclear power reactor to produce electricity. Destructive purpose, nuclear bomb. Okay, we can compare this with radioactive decay. What's the difference in nuclear fission and decay? See, nuclear fission means it's not occurring itself. We are making it. But nuclear decay is a spontaneous process, naturally occurring process. We don't have any control in nuclear radioactive decay. Radioactivity, we don't have any control. But nuclear fusion, we are making it, we are making this process run. Then nuclear radioactive decay, the nucleons emits either alpha, beta or gamma. Okay, alpha, beta and gamma. Gamma also is being emitted, but it's not large, it's not very large. But in the case of fission, see, huge amount of energy is being released. Fission compared to nuclear reactivity, the energy means gamma only, the two are particle. But even compared to gamma, huge amount of energy is being released in the case of fission. Then see, the decay is spontaneous and we can't control. But in the case of nuclear fission, we can control and use it for the energy production. Fission is controllable and we can use it for the production of energy. Okay. So students, you have any doubt regarding fission, you can ask now. Okay, raise your hand. If you have any doubt regarding fission, you can ask now. Process, example, controlled, non-controlled, comparison between radioactivity and reaction, how this energy is obtaining. How this energy is obtaining? Mass difference. When the uranium split into barium, krypton and neutron, a small portion of the mass is missing. That missing mass is converting into energy. Any doubts? Students, we are studying another process as nuclear fusion. Okay, so regarding fusion, I will show you a video. Nuclear fusion, next process. Okay, students, I will show you an example of nuclear fusion. Fusing means combining. Okay, see, I will give an example. You can see two atoms here, the deuterium and tritium. See, in the case of nuclear fission, previously we discussed nuclear fission, normally heavier nucleus are being involved. In nuclear fission, heavier nucleus are being involved. But in the case of nuclear fusion, see, lighter nucleus are involving. See, deuterium. Deuterium means 1 proton, 2 neutron. Okay, see tritium, I will show you. Okay, sorry, it's a sprotium. Yes, mistake in the video. Sprotium. 1 neutron and a proton, sprotium. 2 neutron and a proton, deuterium. No, sorry. It is tritium. So, deuterium and tritium. Deuterium and tritium, both are combining. So, 2 lighter nucleus combine and form a heavier nucleus. Exactly opposite to the nuclear fission. In fission, a heavier nucleus split into lighter nucleus. Fusion, lighter nucleus combined to form a heavier nucleus. New nucleus is being formed along with this energy. Okay. If you take 1 kilogram of fuel for fission and fusion, the amount of energy released in fusion is heavy. Take same amount of mass, this fusion can be produce more energy. Okay. Even though both are carrying same mass, the fusion can produce same amount of energy. Okay. So in fission, we are using heavy nucleus, energy is being produced. Here, lighter nucleus combined to form a heavier nucleus, both cases energy is being produced. Okay, students, we can study about this process in more detail. Let's see what this process is. So, nuclear fusion means the process in which two lighter nuclei combine to form a heavy nucleus. Lighter nucleus combine to form a heavy nucleus. Such process is called nuclear fusion. Again, there is a missing in mass. That mass will be releasing in the form of energy. See in your textbook page number 304. You can see so many reactions. Okay, I think all 4 examples for nuclear fusion reaction, 6 reactions are given in the textbook. Each of the reactions should be studied. Okay, each reaction you need to by heart. In the case of fission, there is only 1 reaction is given. So, see, one reaction is given as a blue table and two more reactions are given. So all the reactions given in the test group regarding fission and fusion, you should be by heart. Okay, not only from blue box, all the reactions given related to nuclear fission and fusion, you should by heart. Okay, regarding this fusion, 6 reactions are given. Okay, see first one, deuterium and deuterium, helium isotope is formed. Again, helium and deuterium and another helium with mass number 4 is formed. Then protium and protium, deuterium is formed. And deuterium, tritium is formed. So all these processes are fusion. Not only see in the case of fission also, it's not only one reaction. Whenever a heavy nucleus split into daughter nucleus, all the processes are fission. Whenever lighter nucleus are combined to form a heavier nucleus, all these processes are fusion. So fusion is not possible. See, till now we can't able to control it because it's not possible in ordinary temperature and pressure. But it's occurring, it's naturally occurring in all stars, including our sun. See, fusion occurring in all stars, including our sun. Why we can't able to use it? Because till now it's uncontrollable. Huge amount of temperature and pressure to trigger this process. So almost equal to an energy produced by a normal atomic bomb. That much energy we can't able to control. But still fusion is a source for future. Somehow if we can control it, what are the advantages we are obtaining? Somehow we are capable of controlling this nuclear fusion. See, both reactant and products are safe. There are no radioactivity at all. First is a clean fuel. Then comparatively less amount of fuel need to be stored because large amount of energy is being released. So more efficient, less pollutant, means almost non-pollutant. Then obtaining hydrogen is easier than obtaining uranium. So comparatively easier to get the fuel. So in this manner, fusion is a source for the future, but till now we can't able to control it. This occur means almost 1/6 of earth will burn. So we can't make it possible. So till now we can't able to control it, but still it's a source for the future. So we can just compare these two, nuclear fission and fusion. See, fission, what's the condition? When a neutron bombarded with a heavy nucleus, fission will occur. But fusion requires high temperature and pressure. In high temperature and pressure, lighter nucleus compared to form heavy nuclear fusion. Fission reaction is possible in ordinary temperature and pressure. We can start fission in any temperature and pressure. But nuclear fusion requires high amount of temperature and pressure. See, nuclear fission reaction nearly 190 mega electron volt. One fission, nuclear fission, 190 mega electron volt is released. One fusion produce almost 24.7 mega electron volts. Okay, see, single atom if you consider, fission will produce more energy. Okay, but you know that uranium is almost heavier, almost 235 times heavier than hydrogen. So if you take a mass, means fusion will produce more amount of energy. Single reaction, fission produce more energy, but amount if you take number of atoms or particular weights, fusion will produce more energy. Okay, see that fissionable substances are limited in nature, but fusionable substances are, see, hydrogen is almost, now hydrogen is almost 90% of universe is hydrogen. Universe. So in universe the fusionable substances are huge in amount. Then about pollution. See, in the case of nuclear fission, both the reactants and products are radioactive. But in the case of fusion, both the reactant and product are non-radiative. Better clean fuel. It's better clean fuel. Then fission can be controlled, but fusion uncontrolled. Fission based on nuclear bomb, but fusion hydrogen bomb. You may have heard about it. Hydrogen bomb is based on nuclear fusion. More powerful than atomic bomb, which is exposed in Hiroshima and Nagasaki. Highly dangerous. Okay, so our chapter is over. Okay, any doubts regarding this chapter? You can ask now. This section, fission and fusion, very small section only, very easy topics. So you can ask any doubt now. Okay, students, study properly. Hope you remember. Students, take page number 303, 302. There you can see the reactions at the middle, just above that box, almost at the middle. Two more reactions are given. Okay, see, one reaction we have discussed here, and two more reactions are given in the rest book. 302, left side, middle. Okay, both are starting with uranium, but reactions are different. Okay, see, two reactions are there. Total two reactions are there given in the rest book. So all the reactions should be by heart. Then at the end, yeah. Equivalent mass means, see, energy can be converted into mass and mass can be converted into energy. When mass converting into energy, it's become a huge number, huge amount, that much only, an equation. Chapter is easy to understand and learn. So study properly. Remember test paper soon. I will conduct test paper. Get ready for it. Get ready. Study the sound chapter properly. Okay. As soon as possible, we will conduct a test paper. Okay. So thank you. See you in next class.